Hello everybody. Today we shall discuss the concepts of canonical transformations. But before we go there, let me remind you of a few things about the Lagrangians. One is the Lagrangian point transformations. And let us take this up using examples only. You already know all this. So what is a Lagrange point transformations? Lagrangian point transformation. Well, we have a configuration space, and this configuration space is, say, given by the generalized coordinates q1 to qn, n of them. So the degrees of freedom is n. And the point transformation takes from one set of these generalized coordinates to another set of generalized coordinates. So let's say capital Q's. Again, degrees of freedom is obviously the same, so there are n coordinates. So that's what we mean by Lagrange point transformation. It turns out that in some cases it is quite useful. The degrees of freedom, though, is the same, the system in different coordinate systems may behave a little differently. Well, the system behaves the same, the mathematics may become easier in certain coordinate system. Take the example. So, example of two-body central force problem. So, central force means that the potential will depends on the separation of the two bodies only. So this central force problem, let us write it down first, choosing the two bodies. So say I have one here and the other here, and I choose an origin there. So I just write the radius vector with respect to this origin. x1, say the body has a mass m1, this is m2, and the radius vector is x2. Okay, so now if I try to write down the Lagrangian for this system, you will agree that the kinetic energy is half m1 x1 dot square plus half m2 x2 dot square. And the potential energy depends on only the separation between them, which is this. Right? Now, this is a generic term. I have not actually chosen any coordinate system here. I just written in terms of the radius vectors. So let us now, if I write in if I want to write this in, say, Cartesian system, so then my x1 is given by, say, the three Cartesian components x1, y1 and z1, and x2 is given by three Cartesian components x2, y2 and z2. And you know how to write it down. I will just write down the potential because that is what we will have interest on. This is x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square to the power half. So it depends on that, right? So it's a 1 by r potential is just 1 by this entire thing. square bracket to the power half. So which means Lagrangian depends on, L depends on all 6 coordinates. You see, this is a system with 6 degrees of freedom. There is no degrees of freedom, there is no constraints here. So the degree of freedom of this system is 6. And the Lagrangian also depends on 6 coordinates. So it does not have any cyclic coordinate. It has all the 6 coordinates. So no cyclic coordinate. Right? But you see, this is a system which is, we are not considering any external force acting on it. So you know that the center of mass of the system is not supposed to be accelerated, right? That we know from our usual classical mechanics ideas. So if I now write this in terms of a different types of coordinate system, which is called this center of mass reduced coordinate system, where I have two vectors. One is capital R, which points towards the center of mass of this, and capital M is the total mass of the system, M1 plus M2. And then you know that if there is something we can define called the reduced mass, which is M1 R1 plus M2 R2 by M1 plus M2. I'm not writing it explicitly because you are advanced students, presumably know all these things. And then the reduced mass vector. So the smaller is nothing but the distance between the two particles now. So smaller goes from one to the other. If you wish, it is like this. Which means now the potential only depends on modulus of smaller. And then there we get a remarkable simplification, because now L does not depend on capital R explicitly, three components of R are cyclic. Well, that is amazing, right? You just changed. So what has happened is that you have just changed the coordinate system from Cartesian to some reduced center of mass system, and then you realize that there are 3 cyclic coordinates. And you know that what is the importance of cyclic coordinate, because you will get to the conjugate momenta corresponding to R, which is conserved. And if the conjugate momenta is conserved, then for these 3 coordinates R, you don't need to solve a second order differential equation. You can solve 3 first order differential equations, and they are also straightforward to solve because PR is constant, so P can be depends on what is your PR, but in certain coordinate system it can be just something times T plus constant. So now this tells us that if I can choose the cyclic coordinates, if I can choose the coordinate system properly, if we can choose the coordinate systems properly, now this properly, I am keeping an exclamatory marks here, we'll come to it shortly, why I put that. The problem becomes easier to solve. I think you will all agree to that. But this properly is a big question, because how do we know a priori that what is a proper coordinate system? And at present, we don't have any answer to that, because there is no guiding principle to know the proper coordinate system. Okay, so this is one recapitulation that I wanted to do. And then, so this is about Lagrangian point transformation. And it shows that for the degrees of freedom, when it does not change, we can actually choose coordinate systems where some of the coordinates are cyclic, and it becomes easier to solve. Now let us go to the, let me remind you the same thing for the Hamiltonian systems. So Hamiltonians and cyclic coordinates. In the case of Lagrangian, remember that if L is independent of, if L doesn't depend on a particular coordinate, in this case 3 of them, then the corresponding momentas are conserved. So in this case 3 momentas are conserved. Similarly, what happens for the Hamiltonian? So if I have a Hamiltonian which is a function of the all Qi's, Pi's, and say also of time, just let me remind you of the notation here. So the notation, this is what is widely used. In the left hand side, I have a number which I get if I use this operator or this function, and the function that depends on these 3 variables. Okay, so this h over here is different than this h over here. So that this h, the h in the right hand side stands for a function, the h in the left hand side is the value that you get if you put the values of qi, pi's, and then t in that function. But nevertheless, so this is my Hamiltonian, and if my Hamiltonian is independent of the kth coordinate, so that essentially means this is 0. So this is a mathematical statement which essentially means h does not depend on qk explicitly. That's the partial derivative for. Right? So h doesn't depend on qk explicitly. But canonical equation tells you that pk dot, the rate of change of the momentum pk, is nothing but minus del h del q k, and that is 0, and that implies that pk is constant. So pk is the conjugate momentum. Remember that. Okay, so let me show you that also, that pk is the conjugate momentum. Remember that the canonical action, or let me write the canonical Lagrangian, which he wrote with a mirror L. This is a function of all qk's, or should I write qi's? K stands for a particular one which is constant, which is not there explicitly in the Hamiltonian. Qi dot, pi dot, t. This is what? This is pi qi dot minus h, right? And by definition, conjugate momentum to say QL, what will this be? So this I will call PL is by definition del L del QL dot. QL dot only exists in the first term, the kinetic term. So this is PI. This is the same thing as this. So let me put this with a bar over here. So that this P, whatever stands here, is essentially the conjugate momentum. So this P is the conjugate momentum of this coordinate Q in this particular case of the Lagrangian. So what do I get from here? So I see that if the Hamiltonian is independent of a particular variable, particular coordinate, doesn't depend on that particular coordinate explicitly, then the corresponding conjugate momentum is conserved. So it is just like the Hamiltonian case, Lagrangian case. Now, why is it important? It is important because this may be very useful for us, as we will see, while solving the canonical equations. Let me just show you one more thing here. So what happens to the action? So the action is given by L dt. And now what I do is I take out the parts. So the Hamiltonian depends only on certain q's. So I only keep, so if I keep the Hamiltonian here, so this doesn't depend on one particular q or few particular q's, which are qk's. The qk's, which has a conjugate momentum pk, I can keep those separate because they may come without the Hamiltonian, and for those I can even take the pk outside because it's a constant of motion. So it doesn't depend with time, and the integral is over time. So I get pk qk dot dt here, and rest of the kinetic term I can keep here, right? If I do that, you see that delta A equals 0. When I will do, this term will not contribute because this term is nothing but qk at the endpoints. Qk dot dt is dq, so dq integral is q at the endpoints. So this essentially means the delta of this entire thing equals 0. So which essentially shows you explicitly that if you have found some cyclic coordinates, then your problem becomes a lot easier to solve. You don't need to even bother about those cyclic coordinates, variation of those cyclic coordinates. Now, assume we have done a point transformation this for the time being is fantasy. Okay, so we are assuming that we have been able to do a point transformation which preserves which makes all PIs constant. Okay, let's have that fantasy that we have by some miracle have done some point transformation where all PIs are constant, so say alpha I. Nobody told you that you will be able to do that all any time, but we will see whether we will be able to do. But if we can do, then so all these are constant. So I have h, which is function of what? So if all pi's are constants, I cannot have h function of any of the coordinates, because all conjugate momenta are constant, means that all the coordinates must be absent from the expression of h. So all it can be a function of is all the alphas. And well, it can be a function of time as well. So if I calculate any of the qi dots, what is that given by? That is given by del h. Well, I don't need to calculate the pi dots because they are all 0. So let me just write that here. So pi dots are all 0. And what about qi dots? So qi dots are del h by del corresponding pi, which is the pi's are alphas. So del h del alpha is. You see, that also has to be a constant. Okay, so not need to be explicitly if the Hamiltonian depends on the time. So let me remove the time dependence for the time being. Okay, so if you can put in the time dependence, but you will see that it is easier to solve even then. But let's just for understanding purpose just say that, okay, if the time dependence is not there, so del h del alpha I now depends on all the alphas only. All the alphas are constant, so del h del alpha I has to be a constant. And if that is the case, this is absolutely easy to solve, because if I call this constant some beta I, so then qi dot is beta I, which implies that qi as a function of t is beta I t plus some gamma I. So these are integrals of motion. Or initial conditions, if you wish. Linear, so simple. Even if it was h was a function of time, still you will be able to solve this, because beta is a function of time then. So if h is a function of time, if h depends on time, then this is dqi is h. So then this not h, sorry, so this will be beta, but that will be a function of time now. So this is beta as a function of time dt. And again, you can solve this. You have to do the integral still, but you can do it trivially. A lot more easier than if you have to really solve a differential equation. So that is, if that fantasy can be achieved, then it will be amazing. We can just do coordinate transformations and solve the differential equations, solve the canonical equations so easily. Okay, so can we do that? And that is what that type of coordinate transformations are called, the canonical transformations. What is required for these coordinate transformation? Well, you see, even after the transformation, we said that we have done some transformation and we have achieved the fact that all pi's are constant, but afterwards we are using the canonical equations of motion. So we need, so these cannot be any coordinate transformation. These are the coordinate transformations where the canonical equations remains invariant. So what are the requirements for this fantasy? What are the requirements for this to work? First of all, so let's start with the point transformation itself but now for the phase space. Okay. And let us also assume the Hamiltonian is not a constant of time. Sorry, Hamiltonian is independent of time. This is just for simplicity to start with. Okay, now with these two, let's ask the question, what is the space in which we are doing the point transformation? So remember that the point transformation now, we are talking about the transformations in terms of the canonical equations, the Hamilton's equations. So the point transformation is on the phase space, which means I have these 2n coordinates qi and pi. I call them collectively coordinates. I'm not writing the time explicitly because we have assumed that the Hamiltonian is independent of time. And these are going to 2n, say capital Qi and Pi. So when I showed originally the point transformation here, we did not write any here. We did not write any Qi's because we are doing Lagrangian mechanics here. But see, I also have a Lagrangian I also have a canonical Lagrangian. So I can do a point transformation for the coordinates of the canonical Lagrangian, which is what I have just written here. So the point transformation is happening in this space. But there is one more thing that I need the canonical equations invariant. I need to have the same canonical equations so in terms of QIs, I should have these as written some del H say prime del Qi equals minus capital Pi dot and similarly del H prime del Pi equals Qi dot. Okay, I want that. This needs two things to be not changed. So one way to achieve how can we achieve? Well, these equations came from an action. The action was written this way. L, the mirror L, which is Pi Qi dot minus H, which is a function of Pi Qi. I should write Qi Pi, but all right. Okay, so it should have the same canonical form. The Lagrangians should have the same form, because that is the form which gives rise to this canonical equations. If we change the form, if I, for example, put in pi dot square, then I will not get the same equation. And we needed to have the same equation because that is what we used here. So in terms of the new variables, after we said that we have done all this, made all the momenta conserved, we still use the two canonical equations. It's not only that, you see, these two now has to be identified. So I need to have pi qi dot equals pi qi dot. Not necessary. It's not a necessary condition, but sufficient. And if this two, so what do I mean by not necessary but sufficient? I mean that if this happens, then this will work out. This will work out. It may still work out. This may still work out if that doesn't happen. So that means that it's not sufficient, but it's necessary. So we'll see, and we'll see. Go to more general cases later. And if this is true, then my Hamiltonian functions are same. Okay, so this h and h prime are same. Okay, so that is, so these two if I can have, then this is satisfied. But a more general case will be if I look at these. So let's say pi qi dot, and I have a dt over here. So this is essentially pi dqi, right? So this, what is conserved, if you see more carefully, is this integral of t1 to t2 pi dqi. This is conserved. Which means that this equals, when I write it in terms of the transferred coordinates, this is equals to that. So that, but that doesn't require the differential forms to be conserved, because I can always add to it any function. Okay, let me not put it there, but then if I write this pi dqi not equals pi dqi only, but add a differential, total differential of some function s. This is total differential of some function. Then what will happen? So if you just not look at the part of the Lagrangian which depends on the Hamiltonian, or if you look at just this part, so when I will integrate it between t1 and t2, I will just get again s at the endpoint. So s at t2 minus s at t1, And when I consider the variation, this variation by the endpoints, we don't have variation of anything. So this is essentially 0. Well, I will be able to call it 0. We'll be able to call it 0 if S depends on the coordinates only. So coordinates in this case, it may depend on all the QIs, but it can also depend on all the capital QIs, because I can put this in the integral in either this side or in the integral in this side. So wherever side you put in, you have to write the variation with respect to the coordinates at these 2 points, and the variation with respect to these coordinates you chose to be 0. There is no variation. If I say, then I can put this 0, and then I can add this arbitrary function ds to these differentials. So S is a function of, S is a function of all Q's and all capital Q's. So now what I can do is I can choose my S, and that will generate a transformation of the coordinates. So I can choose S, and that will generate transformation of canonical nature. Why I say canonical nature? Because that will preserve the canonical equations, keep the canonical equations invariant. So this, because of this, S is called the generating function. Okay, so if you remember that Pi dqi equals, say, Pi dqi plus ds, and S depends on all small q's and all capital Q's. So if I can write this, the differential of S as and if I put that back in here, so I will get a relation between certain things. So let's see what I get. So I can put these two in the left hand side, because that will make our comparisons easier, and ds in the right hand side. So I get del s del qi dqi plus del s del qi dqi. So you see that if I collect the coefficients of q's, why can I do that? Well, because they are completely independent set of coordinates. One is in one transform form, the other is the other transform form. So they must not mix with each other. So I get this. Okay. So what are these? Why are these important? So let us go back a little bit and try to understand that, and so that will give us quite some insight on why we are doing and how we were doing the canonical transformation. So here we said that S is the generating function which depends on all Q's, which means that I can choose my S to generate a certain type of transformation, right? Now the question is that if I choose a S, what are the transformations, or the vice versa? For example, if I wanted my new canonical momenta to be constant, should I choose S in a certain way that this Pi becomes constant? And that is one of our goal, that is one of the examples that we show earlier. Well, it turns out in this form, when I write S, I get these two equations, these two relation between the, so this Pi, which is the old canonical momenta, given in terms of the old, the differential of S with respect to the, not the differential, the partial derivative of S with respect to the old coordinates. The new momenta is given by the partial derivative of S with respect to the new coordinates. So there is some mixing of the coordinates happening here, by which I mean that if somebody tells me S, I cannot directly get what is Pi, capital Pi, out of that S. Maybe it was more useful if small pi is given as a derivative of S with respect to capital, say Pi, and small qi is given as a derivative of S with respect to capital Qi or something, which will tell us the new coordinates in terms of the old coordinates. Okay, but that is not the case so far, but you will see that it can fix it. Okay, so that probably we'll do in the next class, next discussion. But let me tell you a little bit more about uh, this form. So what this gives is that for such transformations, for such canonical transformations, I have Pi dqi in one side, and in other side I have Pi d capital Qi. Remember, this came from the fact that our canonical equations must remain invariant. And if I consider this, then if I consider these to be same, then what does it mean? Well, just consider that I equals to 1 for the time being, which means I can now draw the phase space over here. So I have only one Q and only one P. So I have a value of P here at a certain time, and I consider a delta Q or dq. So Pi dq is essentially this integral. The integral is this area. Right? Remember that I can have a closed curve in the phase space. If I consider any trajectory in the phase space which is closed, then this integral is a closed path. This integral will give us the area under the path. Or should I say inside? And this constant sign is telling you that I may have another Q and another P. The area here and the area here are same. So the area under a closed phase space trajectory doesn't change in a canonical transformation. Okay, so I think that I will leave you with this today, and we'll discuss on canonical transformation